All right, can everyone see my screen and hear me? Hopefully that's fine. All right, first of all, thank you very much for this kind invitation to speak here. Very sorry, sincerely apologize that I cannot be there in person, but I wish that I could. But anyway, so today what I'd like to do is to share with you some research that I've been doing, which I'm very excited about, which is exploring the frontiers of quantum many-body dynamics, which has been enabled by the development of new quantum technologies called noisy intermediate-scale quantum devices, also called NISQ devices. So specifically, I'll talk about a new perspective to quantum thermalization and how this quantum simulators and quantum devices can give us a new non-equilibrium universality. These are my collaborators, and this talk is based on these works around here. So to set the stage, I'm sure everyone knows that we are currently in this global race, exciting race towards building new quantum technologies. And currently we have very large scale platforms called quantum simulators, in which we have very good microscopic control over individual parts, and they're very large as well. And so these platforms, how you can understand them is that you can think of them as rudimentary quantum computers, and they're not quite there yet. We can't perform arbitrary universal control, but nevertheless, they are very good platforms. But if we only think of them as the first step, the first generation proof of principle quantum devices, then we are missing out quite a bit of what they can give us. So these systems are also very unique quantum many-body platforms that can yield very rich physics. And a lot of it is based on two interesting capabilities that they have. The first is that they are very well isolated from the environment. So they are undergoing unitary time evolution by themselves. And we have also very good control over their evolution at the individual level. So this makes them very different from the traditional condensed matter or solid-state systems that we're used to, in which usually the system of interest is placed on a substrate, and we always have to think about the effects of a bath on it, and perhaps you can't really drive the system too far out of equilibrium because the system always tries to tend towards equilibrium. So all that is to say that these platforms can really explore the very far from equilibrium frontier. Now, the other capability that these systems have is that the way that they give us information is also very different from the way that traditional material experiments give us. For example, they give us microscopically resolved measurement information. So they can allow us to take snapshots of the entire quantum system in one go and measure where each particle is at each point in time. So of course, with this new capabilities, there have been many advances, many new directions have been talked about, and let me just flash for you a few of them. So we've heard about many-body localization from Boris yesterday. And so this has been studied in a optical lattice with cold atoms. And so we have also talked, so there's also been work done on new phases of matter in dynamics called discrete time crystals. People have also realized anomalous Foucault topological systems with ultra-cold atoms. So by driving the system, you can realize topological block bands. And also we have examples of initial states which do not thermalize, which are not ergodic, called quantum many-body stars. And so all that is very interesting, and it's this new field of quantum many-body physics enabled by quantum simulators. But what all these examples have in common is that they all rely mainly on the fine control and well isolation of these systems, and they don't really utilize this new capability of the microscopically resolved information. Now, to explain what this is really about, so let me explain to you how we take data in a quantum simulator. So what happens is that in many of these platforms, we take a global snapshot of the system and we obtain a bit string, Z vector, which corresponds to a bunch of zeros and ones. And what they represent physically is the occupation number of, say, a site, whether it's occupied by an atom or not, or if you have an array of atoms, whether the atom is in spin up or spin down. And so what we might get in a typical run of the experiment is many, many bit strings like this, Z1 being a random bit string, 0101, Z2 being a different bit string. Now, the question is, what can we do with these measurement data? So of course, one can decide to focus on a single site here and estimate the expectation value of a local observable, as we would usually want to do in condensed matter or solid-state systems. This represents, for example, the local order parameter. And if one really wants to be more fancy about it, one can also decide to focus on, say, two sites, ignore the rest of them, and probe, say, correlation functions. But what you clearly see from this is that there's a lot of information which is being thrown out if we only look at local observables or correlation functions. So if there's only one take-home message you should have from this talk, it is that learning how to process this new kind of information that quantum simulators can give us give rise to new opportunities for physics. And in this talk, I'll describe a new perspective to quantum thermalization enabled by such new information. Now, to give you a background about what quantum thermalization is, a very quick background, suppose that you have a closed quantum many-body system prepared in a simple initial state, which is out of equilibrium. So the many-body eigenstates are very complicated. And of course, a factorized state would not be a many-body eigenstate. And we let it go in time unitarily. So we assume that it's not coupled to any path. We know that it's going to evolve to some typically complicated entangled state with many entanglement between different regions in space. So we see that a pure state evolves to a pure state under unitary time evolution. And the key question in this field of quantum thermalization is, how does thermal equilibration arise in a closed quantum many-body system? The system clearly is not equilibrating at a global level. So in other words, the question becomes, how do we reconcile the fact that quantum unitary dynamics, which is reversible and information preserving, is compatible with statistical physics, which tells us that entropy always increases and we have irreversible dynamics? The resolution, of course, is that we should not be looking at a global system, but we should be looking at local systems. So imagine that we have a small system of interest A, and we divide the entire system into A and its complement B. So the intuition here is that B serves as a kind of heat bath for the small subsystem A, even though in totality the entire system is still a closed quantum system. So if we ignore now the state of the bath, which amounts to taking the trace over the wave function, we get a reduced density matrix, and we can ask what is its behavior over time. And the expectation from the second law of thermodynamics now says that we should expect that the local subsystem maximizes its entropy. And in this case, what entropy means is the von Neumann entanglement entropy between A and B. And so it should maximize it subject to any conservation laws that the entire system might have. And in the case of, say, energy conservation, then we might expect that the form of the reduced density matrix tends towards a Gibbs state with some well-defined inverse temperature or temperature set by the initial energy of the state. So this is a very fascinating topic, and I'll not go into detail about how this happens. Of course, there's many works about this, like the eigenstate thermalization hypothesis, and also works about how this condition can be violated in, say, many-body localized systems. But what I really want to focus on is how do we go beyond this framework? Because there's a very key assumption that goes into this quantum thermalization framework, which is that we ignore the state of the bath, and that's tantamount to tracing out the system in a mathematical prescription. So why do we have to do this? Well, in a typical solid state or condensed matter system, this makes sense. We don't really have a full understanding of the substrate of the bath, and so it makes sense to say, let's eliminate all the degrees of freedom. But in these new generation of quantum systems, quantum simulators, we get global information about the system. And we can study quantum thermalization with them. And what we do is that we can divide the information that we get, the bit strings that we get, into regions A and B. And clearly what we see is that every time we collect statistics of subsystem A, which we want to estimate, we also know the state ZB that the bath is currently collapsed into. So the bath is in some classical state, and we know what the correlation between this bit string 010 and the classical state of the bath is. This means to say that we can study different objects like conditional observables. So imagine that we can study something like the expectation value of a local observable on OA, on A, conditioned upon seeing the bath being in a classical state ZB. So practically in an experiment, what one does is that one collects all this data, and then one post-processes it and looks at bit strings on the bath with the same ZB, and then asks about the expected value of OA here. So that's why this object here has a label ZB. So what this is a novel hybrid classical quantum observable. Classical because there's a label ZB pertaining to the state of the bath, and quantum because OA is a quantum observable on A. And this is beyond the reduced density matrix. So the question here becomes, what is the theoretical framework to capture such quantities? Let me now introduce the projected ensemble, which was first introduced by these two works about 2 years ago now. And the idea is as such: suppose that you have a many-body system. We're interested in looking at local properties of a subsystem. We divide the system into A and B as is standardly done in quantum thermalization. But now, instead of assuming that B is completely lost, or we don't know anything about it, let's assume that we have a projective measurement result on ZB. We are able to measure projectively this part of the system and obtain a bit string ZB in this process. We know from standard laws of quantum mechanics that the wave function, the global wave function, collapses into now the eigenstate of this measurement device, which happens to be a bit string ZB times tensor product a wave function on A. And this wave function is provided for by projecting out the global wave function into the bit string ZB, or the partial projection of it. Now, this occurs with a certain Born probability given by the overlap into this projector. All in all, there are 2 to the power of NB such states because there are 2 to the power of NB such outcomes, ZB, it's assuming that we have a qubit system. And we can collate all of them and form this collection of probabilities and pure quantum states. I stress here pure, they're not mixed, into this ensemble called the projected ensemble, which consists of 2 pieces of data, probabilities and the pure quantum states. Now, how can we understand what the projected ensemble is? But first of all, because it's a probability on pure quantum states, it's a distribution, and we might imagine that there's a physical picture that we can draw where imagine that this is the space of all pure quantum states, the hypersphere, the Hilbert space, and we are just plotting down arrows according to the probabilities in certain directions set by the pure quantum states. And so then we can ask about the distribution of this pure quantum states over the set of Hilbert space. Another way of understanding this is that it represents one physically motivated way of unraveling the density matrix on A. So if you go back to an introductory course on quantum mechanics, the reduced density matrix or density matrix can be decomposed into a linear combination of projectors and probabilities. Now, these projectors don't necessarily have to be orthogonal. And what we know as a fact is that there's not a unique decomposition into these projectors, but the projected ensemble assigns a physical meaning to the classical label I. It represents a measurement on the path B. So in this case, quantum simulators give us one very good physically motivated way of thinking how to really understand the underlying states of the density matrix. Given that a projected ensemble is a distribution of pure states over the Hilbert space, how can we characterize it? So just like any distribution, we can study its moments. And what it means is, for example, for the first moment, we take each element of the ensemble, and then we form the density matrix associated with it, and then we average over the ensemble. And this, if for the astute, would not be surprised to learn that this is the reduced density matrix on A. So what we learn from here is that this object, this projected ensemble, is more encompassing than the reduced density matrix. In particular, it recovers the standard treatment of quantum thermalization. And since we believe that most systems do thermalize to a Gibbs ensemble when the ETH holds, then the mean is universal. The mean of this distribution is universal. But we also know, generally speaking, that a mean of a distribution does not fully characterize the distribution itself. For example, the maximally mixed reduced density matrix being the identity, which means that all the arrows in this ensemble have a center of mass being right smack in the middle of the log sphere, for example, has many possibilities. You can think of states that underlie it as being uniformly distributed over the entire Hilbert space. Perhaps they are concentrated along the north and south pole, or perhaps they lie all in the equatorial plane. And the reduced density matrix does not distinguish between these cases because it only talks about the average. So therefore, we need to go to higher moments. We need to form what is called the kth moment operator, which is a higher order density matrix. Concretely, what one does is that one takes the element of each element in the projected ensemble, raise it to the kth tensor product power. So this represents correlations between k copies of the density matrix and then average over it. So physically, what it does is that, for example, the k equals to 2 moment operator captures the average value of conditional 2-point functions. So suppose that we have 2 functions, 2 observables OA and OA prime, and we want to evaluate them in the same classical label ZB, and we can ask about the average value of that. Now, row 2 would capture precisely such an information, and this is not captured by the reduced density matrix only. So given that there's universality in the mean, the question that's obvious is there universality in the higher moments or higher point observables as well? We can formulate a conjecture, a generalized statistical mechanical principle. This is just a conjecture. We know that in the case for reduced density matrix, we believe from the second law that system maximizes its local entropy subject to globally conserved quantities. And here the meaning of entropy is at the level of the reduced density matrix. In particular, if there are no conservation laws, like if the system is being driven, so like energy conservation is being broken, and if there's no, say, U1 conservation, then the maximally mixed state is the state that we should expect the system to tend towards. We can imagine, and we can call this regular thermalization. Now, we can imagine that there is a generalized principle that holds as well in the case for the projected ensemble, in which case the system maximizes its entropy subject to globally conserved quantities again, but here the meaning of the entropy is of the distribution of the projected states over the Hilbert space. Now, one very simple limiting case is the case when there are no conservation laws at all, in which case you might expect that the projected states in the ensemble mimic the behavior of Haar random states, which are uniformly distributed across the Hilbert space. And so pictorially, it might look something like this. We can call this phenomenon deep thermalization. At this stage, this is just conjecture, so nothing has been proven yet. But of course, so before I get to the physics of it, let me explain a bit more how to mathematically quantify this behavior systematically. How do we quantify if a system does deep thermalize or not? And so for that, we can employ a tool from quantum information theory called a quantum state design. We can ask if the ensemble of states that we are trying to analyze approaches the Haar random ensemble at the level of each moment k, and if so, that represents a quantum state design. So let me give a crash course on quantum state k designs. I mentioned that we can ask very nuanced questions like, given an ensemble, does it reproduce the moments of the Haar ensemble at the level of the kth moment? So we don't ask anything about higher moments, because of course that requires more refined distributions. Concretely, mathematically, what we do is that we form the kth moment operator of the ensemble in question. This is the stuff I flashed before. And we form the corresponding kth moment operator of the Haar random ensemble. We take each element of the ensemble, and then we raise it tensor product to the power of k, and then we simply average over the Haar measure. And we can now introduce a distance measure between these two density matrices. A standard one would be the trace distance. And we see that and one definition of a quantum state design would be that if the trace distance is exactly 0, we call it an exact k design. And if you allow for some approximate error, epsilon, then we call it an approximate k design. The upshot of this colloquially is that a higher k design implies that the ensemble of states that we have is increasingly in moment k uniformly distributed across Hilbert space. Okay, so with this mathematical background out of the way, now let me talk about some known results about the projected ensemble in dynamics. In particular, does the conjecture of deep thermalization happen? Let me now introduce the results of this work, the first paper that introduced the concept of projected ensembles. So they looked at quench dynamics beginning from a mixed field Ising model, quantum Ising model, which everyone believes to be sufficiently quantum chaotic. Numerous numerics has been done to show that systems of this sort do thermalize to the expected values according to ETH. And so the experiment is as such, numerics is as such. They begin with some state which is at infinite temperature with regard to the global Hamiltonian, and then they let the state evolve for some time under the unitary, and then they measure part of the system. Then they form the projected ensemble on this part of the system before computing trace distance against the Haar ensemble as a function of how long the quench time is and how big the number of measurements that they are measuring out is. So basically the bath size over here. And here's the plot for the first moment. As I mentioned, the first moment is regarding the reduced density matrix. So this pertains to the standard quantum thermalization regime. We see that they focus on the subsystem size of NA equals 3, and with increasing bath size from NB going from 9 to 21. So the different curves correspond to the different bath sizes, with the darkest one being the largest one. So just concentrate on the largest one. And in time, what they see is that the trace distance go down monotonically before saturating due to finite size effects. But if you can imagine that they can push the simulation to larger and larger sizes, then this will go down indefinitely. And this corroborates our understanding that this system does quantum thermalize. What they also showed was that the higher moments, k equals 2, 3, and 4, also showed very similar behavior. And so this represents the fact that there's an emergence of quantum state designs from dynamics. And this is consistent with the idea that there is deep thermalization. So that's great. So it suggests that there is a new universal phenomenon that's happening here. And this is not particular only to this model. They checked it for a few other models. For those of you who are not too convinced by numerics on a computer, let me show you also some experiments. This was done by Manuel Andres's group in Caltech. They have a 10 atom setup of a 10 Rydberg atom setup. Not too important to know the details of what the experiment is, but suffice to say it's a strongly interacting system interacting via density-density interactions, which you can understand as a kind of Ising model. The experiment was also very similar to the numerics. They begin with an initial state which is all zeros, so all factorized, and then they quench the system under the natural Hamiltonian of the system for some time t. Then they collected all the bit strings. They measured the entire system and collected the entire bit string Z, which then they divided into two parts, ZA and ZB. So the data that they collected looks something as such. ZA is this blue region and ZB is the complementary region. What they looked at was the probability of how often this bit string ZA occurs, conditioned upon the fact that the bath is in a particular state. For example, suppose that ZB was all zeros, all down. Then they looked at the distribution over the bit strings ZA, and they kind of plotted the histogram. So mathematically, this is given by the overlap of the projected state in the bit string ZA. They repeated the process for a different classical state of the bath. So they condition it differently. You get a different distribution. And all in all, you get many, many distributions depending on how many states you have in the bath. Lastly, they looked at the distribution of the probabilities themselves, now ignoring the label ZA, over all these different ZB values. Now, if our belief that the system does deep thermalize is true, then that means that this projected states psi of A of ZB, if it behaves like a hard random state, then we have a very strong theoretical prediction that the probabilities should behave according to what is known as the Porter-Thomas distribution. This is a well-known distribution that has been used extensively in randomized benchmarking of quantum simulators today. These are the results. The bars represent the experiments, and the black line represents the theoretical prediction. The theoretical prediction is the Porter-Thomas fit. There's a Porter-Thomas distribution prediction, and I want to stress that there's no fit in this data at all. So what they show is what we see is that the experiments really match the theoretical predictions without any fudging. What it also means physically is that the projected states are indistinguishable from hard random states as far as Z projections go. Now, these two experiments, one numerics and one actual experiments, strongly suggest that the phenomenon of deep thermalization is a real one, and it appears to be quite universal. It occurs across many different systems, and it's a new phenomenon. But they are only hinting at what happens. So one burning question that one might have is, what's the mechanism of deep thermalization? Why does it happen? And can we really rigorously justify that it happens in some exactly solvable models? Can we really pin down that this happens at least in some specific examples? And that's the purview of these two works here, which I did with my collaborators. In my first work, we looked at a periodically kicked Ising model in 1D. So periodically kicked meaning to say that it undergoes Fouquet dynamics. And the dynamics consists of two parts. The first part is by interactions under Ising interactions, nearest neighbor interactions, and a longitudinal field with some strength G. The second part is a kick in the Y direction. So traditionally, Ising model is written in the X direction, but this is not too important at all. So we kicked it in a Y direction for some strength H. And then we repeat this process. This entire Fouquet unitary UF is repeated T steps. The initial state is given by all classes. And now we divide the system into two parts, NA and NB, and we're going to measure the B system in the Z basis. And then we're going to construct this projected ensemble on this small part. Why do we choose to look at this model? Is because previously this model has been shown to be what is known as maximally chaotic, in the sense that its spectral statistics, its spectral correlations can be rigorously proven to obey those of random matrix theory predictions. So we were looking at this model because we kind of thought that this should be a very prime example for a model that can be used to prove deep thermalization. Indeed, if we let the couplings, the Ising couplings, be specific values like j is pi over 4, and the transverse kick be pi over 4, and we allow for arbitrary longitudinal field as long as we stay away from integer multiples of pi over 8. And this is necessary because we want to stay away from the free fermion limit. We also want to stay away from the Clifford limit when this is pi over 4, when dynamics is not scrambling enough. So as long as we stay away from those points, what we can show rigorously is that when the quench time t is larger than or equal to the subsystem size of interest NA, then as long as the bath size is infinitely large, we show that the kth moment operator of the ensemble matches exactly the kth moment operator of the Haar random ensemble. Let me stress that this is a really remarkable result because this is saying that in a short amount of time, t that does not scale with the entire system size, but only scales with the system size of interest, and so it is order 1 in total system size, meaning to say that the state is very lowly entangled and has an error law entanglement. Nevertheless, what measurements do is that they allow us to create an ensemble of states here, which can be rigorously proven to mimic the behavior of Haar random states. And so this is a concrete example of deep thermalization happening. To flesh out some numerics, so here we looked at a system of NA equals to 3, and the bath size being 100, which is sufficiently large in this case. And this is the distance to the Haar distribution over time, over quench time. Initially, they start up quite high because they're far away from the Haar ensemble. In each moment, k equals 1, 2, and 3, and 4. But magically, all of them dip down to be 0, or very small, at this magical time 3, which matches the system size of interest 3. So this is where certifiably pseudo-random states can emerge. How can we understand what's happening in this model? What's so special about this model? So for those of you who have worked with this model slightly, you might recognize immediately that with the parameters that I've chosen, as well as the measurement basis that I've chosen, this model is really special. It has this property called dual-unitarity, or the model is dual-unitary. And I refer to you to works by Tomasz Prosen, Austin Lammercraft, and so on, to describe this very interesting property. Let me introduce what this property is to you in a nutshell. So we are looking at quantum evolution of n qubits for quench time t, and then we're measuring out the system over part of the system. And of course, dynamics in this direction is unitary, it's information preserving. Now, if we write this diagram or this unitary in terms of its local elements, which is what we represent as a tensor network diagram, it turns out that by looking at the tensor network in the direction which is 90 degrees away from the time direction, which means to say that we look at if we look at a circuit this way in the spatial direction, this circuit happens to also be unitary in this direction. So this model can allow us to think of dynamics in 2 different ways: unitary time evolution along the original time direction, as by definition, and it is also unitary in the space direction. If you imagine that there are t qubits, which are t fictitious temporal qubits, which are initialized. And now we can understand what's going on in this system, because what the measurements do, measurements have 2 outcomes, 0 and 1. What they do is that they toggle between 2 unitaries in this direction. If I see the measurement outcome 0, I'm obtaining a measurement, I'm obtaining an evolution by U0, a unitary U0. And if I see the measurement outcome 1, I'm obtaining a measurement, a unitary by evolution U1. Now, at this stage, there's a last map that maps me from the temporal slice to the physical system of interest, NA. And it turns out that for this model itself, this is a perfect isometry. So meaning to say that angles are preserved from here to here. What we see is that measurements induce a stochastic kind of quantum computation by a depth NB, which is the total system size minus NA. So the circuit depth is N minus NA on T temporal qubits. And we're going to think about how this computation can give us Haar random states in the limit when the bath size is very large. What we also show is that this U0 and U1 unitary gates are universal gates. So they're not quite gates they're used to in quantum computation, because usually we think of like two body gates, or a C0 or a CZ. But if I generalize the definition of them, what they really are two unitaries that don't commute. And in fact, a very long product of them, U0 and U1, will cover the entire space of unitaries. And this is what is known as a universal gate. So we know that this deep quantum circuits cover the space of unitaries, and this is what we prove, that they are universal. What's perhaps not so immediate or obvious is the fact that this distribution is in fact uniform, and this comes from a very standard result in probability theory. One can also think of this as a kind of central limiting theorem of long products of unitaries, which are universal from the point of view of quantum computation. So the upshot is that under a very long, large depth unitary, the state that emerges on this temporal slice can be shown to be fully randomized in the sense that they obey the power distribution. And now we're almost done, because there's a last step of sending this information, this randomized information, over to this NA system of interest. And it turns out that in the case when it's a perfect isometry, the hard randomness on this temporal slice translates to a hard randomness on the A system, as long as the sizes match up, that the input is larger than the output. So as long as T is larger than NA. And so we see that there's this physical picture where deep thermalization arises from a stochastic quantum computation indexed or induced by measurements. And importantly, the state that it is performing quantum computation on is an entangled one, which is created in unitary dynamics. So this suggests that a generic quantum dynamics, since we have evidence from numerics and experiments, it also deep thermalizes that generic quantum dynamics would also produce an entangled state that is sufficient for this stochastic quantum computation. And this seems to be a very universal phenomenon. Now, one can, of course, generalize this. And so what's a key property is of dual-unitarity. And we can also look at models beyond the Ising model that have the property of dual-unitarity. So to really quickly explain this, imagine that we have a 2-qubit gate, a unitary gate. Unitarity means that if we compose them U and U dagger, they are equal to their identity. But we can also think of kind of rotating this tensor, this unitary box, and connecting the legs in a different way. So instead of treating input as from bottom to up, we treat input from right to left. And now if you connect them this way, there is a very special class of unitaries that also equal to the identity once you connect them this way, and this is called a dual unitary gate. Now, armed with this, one can write down all the dual unitary gates for qubit systems. It turns out it forms a 13-dimensional manifold, and one can construct quantum circuits, quantum dynamics based on such special gates. And at the end, let's imagine that we are performing a special kind of measurement, which is Bell measurements. Now, what we showed in our second work was that if we sample this unitary gate randomly from this 13-dimensional manifold, then the corresponding quantum circuit, almost all instances of them, a single instance, would form also exact quantum state designs for all k, all moments k, as long as the quench depth T is larger than system size of interest. For those of you who might be who have done a bit of measurement-based quantum computation research, it might strike you as very similar that these states seem to have some sort of computational power, and indeed they are very intimately related to what is known as resource states in MBQC, and I refer you to this new work that we have on the archive. Great. So we have established that this phenomenon is indeed a real thing. It seems to be universal, and we can explain that it happens in some exactly solvable models. But in these very interesting models, regular and deep thermalization occurs at the exact same time. Once the system regularly thermalizes, the density matrix reaches a maximum mixed state, it appears as though hard random states also occur at the same time. So one might question how generic is this property? And so that was the scope of these two works. What we looked at was how generic dynamics breaks the condition of dual unitarity and what effects it gives rise in terms of the Haar ensemble. Now, a generic quantum circuit can always still be thought of as evolution in the spatial direction, because we can always turn our head sideways by 90 degrees, and measurements would induce a kind of computation in the bulk once again before being mapped to this NA system. This we can always do. But once we move away from dual unitarity, then it turns out that the computation in the bulk is no longer going to be given by unitary evolutions. In fact, it's going to be given by, in general, non-unitary matrices. There's also a second effect, which is that the map from this temporal slice to the A system of interest is no longer a perfect isometry, which I claimed for the case of dual unitary circuits. In fact, it's going to be an imperfect isometry. So let me very quickly explain how these two effects can give rise to a non-trivial separation between the regular thermalization time and deep thermalization times. So first, let me focus on the fact that in the bulk, computation is no longer by a unitary evolution. In general, if we have a non-unitary matrix or operator, we can always try to find the best way to write it as a unitary. And this is given by what is known as a polar decomposition. We can always write it as a product of a unitary and a positive semi-definite Hermitian matrix. So this is akin to a projector. And one can imagine that under multiple applications of U tilde, so U tilde is no longer unitary, an input state gets projected to a fixed point state under the action of this projector. This is indeed what happens. So this very simple observation leads us to this fact that, okay, so imagine, okay, so this picture is a bit busy, but let me walk you through it. Imagine that we have a very, very large system that, and then we're measuring out all of the qubits. They give rise to a random pattern of zeros and ones, and that corresponds to different U tildes of zeros and ones, depending on the measurement outcomes. And let's assume that we have, say, 2 or maybe 3 measurement outcomes in which the first R qubits are the same. So this part measurement outcomes are the same, but the measurement outcomes here are different. Now, there is a length scale beyond which the state, different input states at this time slice get projected to the same state. So in mathematics, this is given by the fact that 2 wave functions given by 2 measurement outcomes, ZB1 and being the same on this region of space. But if they have different measurement outcomes on B2, they are nevertheless going to map to roughly the same state as long as this distance is large enough. So there's a length scale which actually happens to grow exponentially with time, the depth of this circuit. And this can be understood from a mapping to statistical mechanical models in the context of exploring what is known as monitored quantum circuits or measurement-induced entanglement phases. So there's a length scale in which 2 input states map to the same state. Physically, what that means is that the projected ensemble therefore only has really 2 to the power of this length scale of states in them, because all the states happen to map to the same state. And so the fact that this ensemble has a finite number of states, roughly speaking, is a constraint on how well it can approximate a continuous uniform ensemble. The upshot is that we have our result 1, and I refer you to our main paper for details, is that we can show that if the time taken to achieve regular thermalization is T1, in particular thermalization to infinite temperature, then the time T infinity to approximate the Haar ensemble, for the projected ensemble to approximate the Haar ensemble, obeys a lower bound where it's given by T1 times the ratio of this entanglement velocity over what is known as the purification velocity. So VE here is the speed of the spreading of local operators under unitary evolution, and VP is the rate at which input states get purified to the same fixed point state. And we can show that there are models in which this can be arbitrarily small while VE is constant. And so there's a non-trivial gap between T infinity and T1. The upshot, the key point is that there exists a non-trivial separation of timescales between how well a system regularly thermalizes and how well it deep thermalizes in general. Our second result pertains to asking what's the effect of this imperfect isometry in mapping the system from the temporal slice to the physical system. Now, let's take the best case scenario where we ignore the effect of the non-unitary evolution in the bulk, and let's assume that it's unitary. And so let's assume that the state here is fully randomized. It has all the Haar randomness that it wants to have. The question here is how well is this randomness transferred to the system of interest under imperfect isometry? Pictorially, you can imagine the situation as such. At this stage, there is a bunch of points on the Hilbert space, and they're all uniformly distributed. And the isometry is going to map you to this smaller space. but it's not good, and it's going to map you to just some small points or some region in space, some concentrated region in space. So in this case, randomness is not fully transferred. The question here is then, how does imperfect regular thermalization, which this picture suggests, translates to imperfect deep thermalization? And so we have our second result that if there is a small non-trivial distance from the reduced density matrix to the maximally mixed state, then there's a corresponding also distance from the kth moment of the projected ensemble to the kth moment of the random ensemble. And we derive this result under some reasonable assumptions. And the point is that this ratio is larger than 1. It has information about the system size of interest, how big it is, dA, and also the moment k. So the key point here is that imperfect regular thermalization gets amplified to imperfect deep thermalization at the level of k. And so this also translates to non-trivial separation at timescales too. And so this clearly shows that regular and deep thermalization are two very different effects. So, okay, so I think I've talked a lot about deep thermalization, and I just want to summarize. Hopefully, what I've convinced to you is that thinking about the new capabilities in dynamics and measurement information in NISQ devices or new quantum technologies can give rise to novel quantum many-body phenomena. But I've talked about deep thermalization, i.e. the emergence of quantum state designs, and how we needed to invent new theoretical frameworks to really explain this, called the projected ensemble. One key point I really want to emphasize is the fact that we have to go beyond our standard frameworks of solid state or condensed matter systems. We had to borrow concepts from quantum information and quantum information. And this kind of marriage of quantum information ideas with condensed matter systems and many-body systems has proven to be extremely fruitful in the past few years. Now, specifically on the topic of deep thermalization, let me just flash some interesting future directions on this. This is an extremely new direction. I'm excited by it, but there's still many things to be understood. What happens if we have finite temperatures? Or more generally, what happens if there are conservation laws in dynamics? Then what kinds of universal distributions do the systems tend towards? Secondly, are there models that exhibit a non-trivial hierarchy of thermalization? For example, they might deep thermalize up to the moment 2 or 3 or 4, but somehow not for higher moments. This would be an interesting kind of hybrid system that really, that from the point of view of normal statistical mechanics does thermalize, but from the point of view of distributions does not thermalize. There's also other interesting questions like what's the relation of deep thermalization times to other aspects of quantum dynamics like scrambling or chaos? Can this be a new definition perhaps of how chaotic a system is? And excitingly also, what other quantum information science applications can we develop that utilize random states? As we know, random states are a resource for things like randomized cryptography, randomized benchmarking, randomized tomography. And in fact, we are currently developing a application based on this new phenomenon going in the guise of randomized tomography. So in a nutshell, what I want to summarize and say is that there are exciting new opportunities enabled by new quantum technologies in the frontier of quantum many-body physics and quantum information science. And I think this is the area where I'm really excited about, and I really hope that more of you would want to join me in this journey ahead. So I want to also advertise that I have PhD and postdoc positions available in my group. I just began my position at NUS in Singapore. And so I invite any interested PhD and applicants, postdoc applicants to apply to me. Please contact me here. Thank you very much.
Okay, thanks. Yeah, we'll have a few minutes for questions. Yes, please. Okay.
Thank you for your nice talk.
Thank you.
My question is about the out-of-time ordered correlators. So I think that is related to higher order thermalization and also intricate design. So is your approach, how is your approach related to the out-of-time order correlators?
Yeah, so that's a great question. Thank you very much. Indeed, in one of the works, we define this new velocity called the purification velocity, which is the rate at which the state gets purified over time. And preliminary investigation suggests to us that VP is actually very related to what is known as the butterfly velocity, which you can get from the out-of-time order correlators. So that's just to us that maybe there's a strong connection between deep thermalization happens to be probing precisely the scrambling of information in these systems. Yeah, so basically systems that scramble information faster from the point of view of OTOX would also presumably then deep thermalize faster as well.
Okay, thank you very much.
Thank you.
Okay, any other questions? Yeah, that's one. Yeah.
In your slides, you show
Yes.
equality where you compare time with the system size, like T larger than N sub index A. So how one can understand this?
Oh, right. How can one understand this? Okay, so for example, the first place that occurs is here when I say that time, the quench time needs to be larger than the system size of interest in order to form this distributions, this uniformly distributed, ensembles. And one can understand why we need this in the first place is because you need entanglement to spread across the system anyway from NA, like say the furthest region away from B. We need this information to spread to B. And this occurs at the rate of speed 1 in these models because the entanglement velocity is 1. Generally speaking, this will be set by T is larger than NA over the Lieb-Robinson velocity, or I guess more precisely the entanglement velocity. So what we need is the fact that in order for deep thermalization to occur, we also need regular thermalization to also occur first. And that is set by how fast an operator spreads in space. The speed at which an operator spreads in space is constrained by Lieb-Robinson velocities. And that's linear, has a linear light cone. And that's why we have this inequality.
Okay, I think that's an online question. Professor, how can you address that question? There's a question from Professor Na.
Yeah, okay.
On Zoom.
Thank you for very nice presentation. And actually, you already mentioned in the summary section, but I would like to repeat the question. So I wonder how this deep thermalization looks like if you consider some finite temperature system instead of infinite temperature system. Do you have some any idea?
Yes. Yeah. Thank you for the question. So let me just go to the summary slide and yeah. So here we're talking about what happens if we know. Sorry.
Yeah, that one. Finite.
Yeah. Okay. So in the case for systems that have a finite temperature ensembles, if the reduced density matrix thermalizes to a Gibbs ensemble with a finite temperature, then we expect that the distribution of projected states would approach what is known as the Scrooge ensemble, or what is known as the Gaussian adjusted projected ensemble. And all those are very fancy name for an ensemble that has been studied in the context of quantum information theory. The key point is that the authors from those works from like 2 decades ago asked the very similar question to what we're asking right now. Given a density matrix rho A at some temperature, what's the distribution of pure states that make that can be used to reproduce it, but which also has the interesting property that it kind of maximizes the entropy of the distribution, or it minimizes what is known as the accessible information from the point of view of quantum information theory. And then they came up with this ensemble. The answer is that the ensemble is what is known as the Scrooge ensemble. So you can think of it as kind of taking a hard random state and then massaging it in the direction of rho A, where rho A is the infinite temperature state. And then you create this ensemble. Numerics has shown that this is indeed compatible, and indeed this is what happens in systems that have finite temperatures.
Yeah, well, thanks. And
Thank you.
I have a very quick question, and there is a special type of quantum states called the quantum antibody scattering states, which are known to violate the regular thermalization hypothesis. So are those states susceptible to deep thermalization?
Right. Yeah, thanks for the question. So deep thermalization is predicated upon achieving regular thermalization in the first place. Without it, you will never ever have, because like deep thermalization refers to the fact that the distributions are uniform, But one implication of that is that the mean happens to be at the center of the Hilbert space, which means that the reduced density matrix is maximally mixed. So if we have a state that does not achieve that, then we should not also expect deep thermalization.
I see. Okay. Okay. Great. Any? Yeah, Sergey. Yeah.
Yeah. Thanks for the nice talk. What is the classical analog of deep thermalization, if there is any? Do you have an idea?
That's a great question. I'm not entirely sure. I mean, because the way that this ensemble is created is via the act of measurements on the system, and the measurements are the ones that are it's the origin, it's the source of this randomness, this distribution. Of course, we could study classical systems and say, let's have dynamics which is noisy, and then one could similarly study what happens to classical states under noisy evolution and consider the entire ensemble of them. Do they cover the phase space or not? I'm not sure if that's directly related to how this randomness is generated in the quantum case from measurements themselves. I mean, like generally speaking, analyzing ensembles is definitely something that one can do regardless of whether it's quantum or classical. But there is a question of, does the act of measurement have a corresponding classical limit in the classical case? I'm not entirely sure about that.
Thank you.
All right. Time. Yep. Anyway, quick. One last question. Okay. Yeah.
Yeah. Thanks for the interesting talk. I have first a clarification. In the projected ensembles, do you take all the possible projectors on subsystem B, including entangled ones? That's for clarification. And the other question is, your sizes NA versus NB, are there any restrictions, or can NA go up to half of, can NA be equal to NB?
Oh, yes, that's an excellent question. So let me first answer the first question. When we construct the projected ensemble, we are choosing a fixed basis on B, which is complete, but fixed. We're not changing them anymore. So we're not considering ensembles of basis on which we're measuring it. We just fix one basis. And usually the basis that we fix is a local unentangled basis, which is motivated by quantum simulators and how they measure systems. Of course, one could study entangled basis, and there are results on that. But I think for me, the more interesting thing is to incorporate locality and measurement basis. Now, the second question is about what's the relative sizes of NA and NB for this to happen. So in all these works, I've considered a finite NA and set NB to be infinite.
Right.
I think we can modify the proofs to have NA tending to infinity, but the ratio NA over NB tending to 0 still. So I think then it still works. I don't know if we can push that limit all the way to NA over NB being half, for example, or a finite value, 1/3 or 1/4. Those are interesting questions to ask. So even in the context of regular thermalization, these questions are also very interesting, and they've been partially asked and partially answered, I think, by Tarun, Grover, and a couple of other people. And I think they showed that ETH was holding all the way up to NA over NB equals to 1/2. And it might be interesting. It would be very interesting to see if deep thermalization also occurs for NA over NB up to 1/2.
Thank you.
Thank you.
Okay, so in view of our need to take a break, I think let's stop here. Let's thank our speaker again.
Thank you.